Hello everyone. Thank you for the opportunity to present to you today about the Trinity Railway Express crossing the Trinity River project. This was a unique project where we had some design and construction challenges, and we had to apply some innovative methods to overcome them. So here's the outline of the presentation. First, I'll do an introduction about our company, HVJ, and then we'll talk about the project background, the geotechnical investigation we did, the design of foundations where we had challenges, and the design of T-walls, and the construction of large offshore shafts in the river, and the construction of the T-walls. So first, HVJ Associates has practices in geotechnical engineering and construction materials testing and pavement and civil design and environmental geology and engineering. Our markets, they include roads, water, wastewater, flood control, airports, ports, rail and transit, and buildings and parks. Actually, there's a picture of the battleship. This is one of the interesting projects we've worked on. HVJ was established in 1985 by Herb Johnson, and in 2016 it became a franchise, and this is the first engineering franchise in the United States as far as we're aware of. So the Dallas branch was sold as a franchise, and now it's HVJ North Texas. That's where I am. And the Austin also was sold as a franchise, and it's HVJ South Central. And we have offices across Texas. Overall, in the whole system, we have more than 150 employees, and we're always looking for new talents. In HVJ North Texas, we are a local North Texas firm. We are HUB certified by the state. We are DBE, MBE, SBE certified by NCTRCA. Our labs are accredited by AASHTO, and we meet the requirements for concrete, aggregates, soils, and asphalt. Our equipment is maintained and calibrated according to regulatory requirements, and our laboratories are climate controlled. Our quality assurance program is centered on ISO requirements for testing labs. Here are some of our clients in the North Texas area: NTTA, TxDOT, DART, DFW Airport, North Texas Municipal Water District, Tarrant Regional Water District, Upper Trinity River Regional Water District, universities like UNT and independent school districts, cities like City of Dallas, Plano, Allen, Frisco, Richardson, and counties. So most of our work that we do is municipal work. So now that we're done with our marketing stuff, we can get to the technical, we'll talk about the project. So for those of you who are not familiar with the Trinity Railway Express, it goes from Dallas to Fort Worth. It's a very fun ride. You should definitely try it if you haven't tried it before. This is kind of like the alignment, how it goes. And our project is closer to Fort Worth. It's east of I-35W. And you can see in the next slide. So this is I-35W on the west side, and the project was between Sylvania Avenue and I-35W. Overall, the project was about 3/4 of a mile of a track alignment. And here's the West Fork Trinity River that we're crossing. The project had 4 bridges, one at Sylvania, one crossing the Trinity River, and then another bridge in this area, and then another one close to 35W. Here's a picture of the existing bridge. This panoramic picture. Of course, the bridge is not curved like this. This is the capability of the iPhone in taking pictures like that. But it gives you an idea. This bridge is an old bridge. It was built in 1903. It's more than 100 years old. Therefore, it requires frequent inspections and maintenance. And it has freight train that uses it, and they have to slow down to 10 miles per hour when they're crossing this bridge. And also freight trains, they have to wait on the bridge to proceed to the next junction. So it causes a lot of delays going through this bridge. The project goals we had were to rehabilitate the existing bridge, since it's more than 100 years old, and then also construct a new bridge so we can have double tracks, so we don't have that much delays. On the bridge foundations, we had some large diameter shafts. Actually, we had 10-foot diameter offshore mono shafts. So these were very critical elements. And we wanted to have minimal impact on the existing bridge foundation. We also had limited right-of-way. So we had retaining walls and we had new embankments that were restricted to be within the right-of-way. And also one of our goals was to have almost no disruption to the existing track operation during construction. So our field investigation, so we did 15 land borings within the limited right-of-way close to the existing tracks. And we did 2 offshore borings in the river using barge drilling. And we had to coordinate with the U.S. Army Corps of Engineers, the Tarrant Regional Water District, TRE, and other railways. This railroad alignment is used by Amtrak, by Union Pacific, and BNSF also, in addition to TRE. Here are some pictures of the geotechnical investigation we did. So we did the work back about 5 or 6 years ago. And you can see in the pictures, we were drilling close to the tracks. We had to go through proper training requirements to be able to walk next to railroads. And we tried to be more than 25 feet away from the tracks, so we don't have to use flaggers. But in the cases where we're within 25 feet, you have to use flaggers, and that causes disruptions in the operation. Sometimes you'd be drilling, and then trains are coming. You'd have to stop, and it causes interruption. That's some of the challenges, doing the work next to tracks. This is the barge drilling we did. So actually, there was no access point, to get the barge in the river. So we used the crane to lift the barge and get it into the river. Another challenge we had to overcome. And you can see on the right-hand side, that's our barge drilling next to the existing footing of the existing bridge. And we tried to be as close as possible to the new foundation location. Just to give you an idea about the geologic conditions at the site, this is in red, this is the alignment of the project. And you can see, this orange looking formation, this is the alluvium deposits, which is normal, it's associated with the river. And then next to it in blue, you can see the Fort Worth limestone and Duck Creek formation. And in green, you can see the Pow Pow formation, which is limestone and Benton clay. And this is kind of consistent with what we've encountered on the project. So we've encountered some soil deposits followed by shale and limestone. These are the boring locations we did. So this is the Sylvania Avenue Bridge, and so we had 2 borings for the bridge. And this is the bridge crossing the river. So we had 1 boring here near the abutment, and then we had 2 water borings offshore, and then another boring on the other side. And then we have borings for the alignment, for the track and for the retaining walls. Then we had another bridge. So we had 2 borings in this area for the bridge, and then we had another bridge on this side. Oops. So here's what we found from the geotechnical borings. This top line here is the existing ground surface. And as you can see here, it drops. So this is where the river is. and this is the east side of the embankment. And then this line here, so this is the shale and the limestone below it. So we drew this line to represent the surface of the rock formation. And that's needed, for the designing the foundations for the bridges, because we're relying more on the rock. But the interesting phenomenon here, you can see, we depicted in the borings we did, was the river. You can see here we have a lot of soil deposits. So this shows the river meandering in this area, and looks like it reached this side where we have limestone, and it kind of stopped, at the edge. Probably it's going to continue moving. It's probably going to take millions of years to deteriorate the rock in this area and keep moving. So the project had 4 bridges across the project. We've used drill shafts on the project, and since we encountered limestone and shale bedrocks, they were interbedded. These are the parameters we used. We used end bearing of 10 TSF to 16 TSF, and we used the unit skin friction of 2 TSF to 3 TSF. And the drill shafts we've used, they ranged in diameter from 24 inches up to 10-foot diameter. And one of the considerations we had was, whether we use permanent casing versus temporary casing. We are, in the alluvium next to a river, with water being there, definitely caving in is a concern. So actually, we've looked into criteria for railroads for casing. So BNSF, which uses this track, they have a design criteria about casing requirements. I apologize, it's kind of hard to read this drawing, but if you're within 25 feet from the tracks, and if you're within this zone, it's called Zone A. Basically, it's at a slope of 1.5 to 1, and then 1 to 1 to establish this zone. So if you have foundations in this area, you're required to use permanent casing, and the casing should be designed for the loads that are caused by the tracks, basically. If you're more than 25 feet away, then it depends on the size of the shaft you have. If it's less than 30 inches, then you just monitor the tracks. And then if it's more than 30 inches, then temporary casing may be needed, or slurry methods would be needed. So the offshore drill shafts, we use 10-foot diameter, single shaft, basically. And the reason we use 10-foot diameter, it's to avoid using multiple shafts and having group effect. This way, using one large shaft, we can rely on the skin friction and end bearing. Some of the challenges, the shafts were installed through the alluvium, going through the mud line, and there's water in there. So we required permanent casing for these. And also the concrete curing near the life tracks was one of the concerns. And definitely the integrity of the shaft. Since we're relying on a mono shaft, it's a single shaft. If it fails, we don't have redundancy. It can be a catastrophe. So we definitely required integrity testing, and we use the thermal integrity profiling. So here's a layout that shows this is the existing track. You can see this is the existing foundation for the track, and this is the new track adjacent to it. And this is a profile showing the new track. These are the drill shafts. We had 2 of those offshore shafts that were 10-foot diameter, and I believe one of them was 61 foot deep, and the other one was, I think, like 66 feet deep. So one of the challenges was to really find out how close we are to the existing foundation. And we didn't know, because the bridge was built in 1903. There are no records since it was built. So we had to do a geophysical study. This is what we know about the bridge. It's sitting on footings actually. So it has the concrete piers. They're founded on or near the bedrock, and we had to do the geophysical study to find out how the shape of the existing footing looks like to get the dimensions. So we used the electrical resistivity tomography. It's a dipole-dipole inverse Schlumberger geoelectrical arrays, and we use 6 traversing lines perpendicular to the southern edge of the footing. That's the area where we were concerned about. We want to know how far the footing goes. So here's what we found out from the geophysical study. Here on the far left, you can see this is the railroad bridge column. That's what we can see above ground. But then the geophysical study, it showed the footing below it, and it extended about 6 feet south of that column. So here's like if you look at an aerial view, this is where the column is, and this is where the footing extended. And here's a sketch that shows it also. So we have about 6 feet of footing below the column. So it was a challenge to locate the new drill shaft. So we went back and forth with the structural engineers, and we're trying to gain as much as we can clearance between the shaft and the existing footing. And it came down to basically being 4 feet away from the existing footing. There are several factors that dictated this. One of them is the limited right of way, and the other one is also the design speeds for trains. But basically, that's the final outcome. We were 4 feet away from the existing footing. And we've required a turbidity fence and oil booms to be installed around all drilling operations in the river to capture any pollutant discharge into the river due to drilling operations. So moving on with the design to the T-walls. They're T-shaped precast walls. They develop strength along the T-stems. We use free draining backfill material behind them. And these kinds of walls, they're really preferred when you have railroad construction because they're fast installation. You just lay down the T sections and you stack them on top of each other. And you have the free draining backfill that you compact. It's a very fast construction, especially with the tight schedule and limited shutdowns. Those were selected as the option. So we had 2 retaining walls in the project, and the maximum height was 13 feet. And we had very limited construction space due to the right-of-way and the active tracks. Overall, we had 1,000 feet of combined retaining walls between the two. So when we design retaining walls, these are the stability concerns we look at. So one of them is sliding, which is the wall wanting to move, sliding in a horizontal direction due to the lateral pressures. Another consideration is overturning, which is the wall just rotating around the leveling pad. And another one is bearing capacity, which is just the soil not being able to carry the weight above it. Notice the difference between overturning and bearing capacity. The bearing capacity is, the wall falls down and rotates, while in overturning it's just rotating about this fixed point. And then the fourth type of stability analysis we do is the global stability. So the whole thing just sliding and failing. These are the minimum recommended factors of safety. For sliding, we look for a factor of safety more than 1.5. Overturning should be more than 2. Bearing capacity should be more than 2. And global stability more than 1.5. So In this design, we have the two tracks above, they're being carried by the wall. The location of the track was very critical because in some cases, if you have a track, for example, on top of the wall, it could help, for example, with sliding because you have a lot of normal pressure that would prevent sliding. But at the same time, it hurts, for global stability analysis. So it was very critical to, identify where the tracks are located and to run those different analyses. So that was an extra variable that we had to consider. Here's an example. Typically, there are many variables that we look at, but the main variables would be the wall height and the strength of the soil underneath. But this was the extra variable we had to look for, is the train surcharge loads. So for example, here's one of the walls. This is the existing track here, and this is the proposed track here. So you can see, for example, here, the distance between the new track and the wall is much more than, for example, in this area. So we had to do multiple analysis, different cross sections, and doing all these different analyses to find. And every time, we had different criteria. Sometimes the sliding governed, sometimes the global stability governed, sometimes it was overturning or bearing capacity. So we had to come up with a solution that worked for all conditions. Another factor we considered in the design, besides the stability, is the eccentricity. So we're looking for eccentricity that's less than 1/6 of the reinforced mass width, or basically for the base pressure resultant to be within 1/3 of the wall. Also, another consideration is the minimum embedment of the wall. It's dependent sometimes on bearing capacity or on stability considerations or settlement consideration or frost penetration. At the minimum, we require a minimum embedment of 2 feet due to frost. Also, shrink and swell is a factor, seismic activity, and scour. Another consideration we did for the T-walls is settlement analysis. So we have 2 walls, and then we have the immediate settlement, which happens pretty much during construction. And then we have the long-term settlement. So, and we determined those without the train load because the train is it's a transient load. But at the same time, also, we determined the settlement with the train load because there's a possibility, for example, the train could break down or for some reason it needs to stop, and you could have a sustained load for a long time. How likely is this to happen? It's probably very unlikely, but it's possible. And we determined the settlement at different times. And you can see with the train load, the settlement is almost double what we had without the train loads. So this is the final design that we came up with. We came up with the stem length, 15 feet for one of the walls and 17 feet for the other wall. And you can see this is like a typical cross section. So this is the existing track, this is the new one, and this is where the wall is. But again, the tracks varied in distance away from the wall, and we had to design for all these scenarios. And the embedment, this is the embedment. We had actually a minimum of 2.5 feet of embedment on this wall. This one we had more embedment, but the minimum we used was 2.5 feet. Oh, and also, this is the under drain shown behind the wall, especially because we were within the floodplain. So that's the consideration. So moving on to construction. So this is the construction of the foundations, the offshore drill shafts. As you can see, the contractor had to build a platform actually to be able to access these locations. And you can see the huge cage. This is 10-foot diameter drill shaft. Here's a picture of the installation, and this was perfectly timed picture showing the TRE the train behind and lifting up the cage to be dropped. And this, on the right side, you can see this is the concrete that was poured, and you can see those yellow cables. These are the thermal integrity profiling cables. They have sensors in them to measure the temperature in the concrete and check the integrity of the shafts. It's a huge shaft, basically 10-foot diameter. So Pile Dynamics is the company that provides the equipment. They provide the sensors, and they came up with the technology. So these are pictures. They're courtesy of Pile Dynamics. They can show you, for example, if bad construction is done. For example, here's a shaft where you can see the cages exposed, and even the concrete inside the cages, there's a void in it. Here's another one. Also, here's a picture, with a group of shafts. So we were very concerned in our case because it's a single shaft. Again, if it fails, the whole thing fails. And being, within the river with water and alluvium, definitely there's concern of caving soil. So we use the thermal integrity profiling. It uses temperature versus depth versus quadrant. Test early after casting. It speeds the construction. You don't have to wait, for example, for 7 days for the concrete to set to do testing. Also, it takes between like 12 to 72 hours. It depends on the diameter and the mix design. And it evaluates the concrete quality, also the cover and the cage alignment. And it avoids false positive issues. It only reports significant defects. So here's a picture also, like how the thermal integrity testing works. So basically, this is the shaft, and let's say the cage is in this area, and you would install sensors, around the shaft, along the cage, all the way down. And if you look at the temperature, how it varies, if you take just a cross section, so the temperature, it's pretty high in the concrete, and then for example, here there's convective heat loss due to air at the surface, and also there's conductive heat loss to soil around the shaft. So you can see the high temperatures are within the concrete, and then they drop down significantly when you're in the soil. Here's a profile that shows, for example, how the temperature looks like. So these are data points that will be collected. And you can see the temperature. Here it's kind of low because we're having heat loss due to air. And it's pretty much consistent, along the sides of the shaft. So that's what you would expect to see. So this is the actual test that we did on our shaft. So this is the cage, for example, you can see in here. And we had 10 columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns of sensors, basically, that were dropped down along the cage through the shaft. And here you can see, the cage and the concrete around the shaft. This is the concrete cover that we were able to find out, based on the test results. So, for example, we had 10-inch concrete cover for the most part. In this area we had about 6 inches concrete cover, and then at the top, we had more cover. That's what you have, concrete that overflows at the top of the shaft. Here's another picture of the analysis. It shows you the temperature. So, for the most part, the temperature is like above 100 degrees. That's within the concrete. So that tells us, all the sensors, they are within the concrete. So we have good cover. At the top, you can see the temperature drops a little bit due to the heat loss, again, at the top, but still we're getting temperatures, around 70 and above. So they did a good job with the construction. Here's a picture of the finished bridge. You can see these are the new columns, and this is the new bridge. It was pretty much at the same elevation as the existing bridge. Here's also another picture showing the new bridge next to the existing one. Moving on to the T-walls. So, you can do all the design you want, and then come construction, something happens, and you get a big surprise. So we had a heavy rain event that happened, and water was ponding, and we were concerned about the soils being softened. So, and we had the problem, we had the limited ability to shut down the existing tracks. We're only allowed to shut it down for 12-hour window, and only few days, I think it was like less than 20 days throughout the whole project duration. So we had to come up with a quick solution. I had to go out to the job site as a geotechnical engineer of record, make an assessment and come up with a solution. So we came up with a solution. We recommended over-excavating the softened soils and then using flex base and geogrid to bridge over that soft material. And also we recommended doing staged construction, where we build the wall like halfway to half of the height. So the soils, even though they're softer, but they can still carry because now they're carrying half the height. And then under that pressure, they would consolidate and water would dissipate and they would gain strength. And then we'd build the second half. So here's the wall actually completed. And we were able to finish it without issues. Both walls actually in those two pictures. So I hope you learned something today. Working with the railroads is really tough on right of way and schedule, of course. We had to apply some innovative techniques, and hopefully you learned something from it and you earned your PDH today. Now I open it for questions.
Hey, Fadi, thank you. This is Carlos Balderrama. First, I want to, go ahead and thank you for presenting to our members today. This is a really cool project, and it's always cool to learn about local, stuff going on in the Metroplex area. So thanks for presenting to us. I have a couple questions. I'll leave my cool one till the end. But is there? I know you said you did a stability analysis for overturning, sliding, bearing capacity, and global stability. Is there a type of failure that is more common in the type of soil that you had out there? Is there one that's kind of you have to be more careful about, or are they all? I know you test for them all, but is there one that maybe is more common?
So sliding was one of the critical ones in this case. And especially because of the terrain. Normally we design retaining walls for highways, but on highways, the kind of pressure we apply is like 250 psf surcharge. With a train, especially this one, we're designing for Cooper E80, so you have about 1800 psf. So that's almost like 7 times that kind of surcharge. So sliding was critical, and also global stability was one of the critical. Overturning was not much of a concern because of the weight we have and the height of the walls. Yeah.
Okay, thank you, Fadi. And then I know you went into the settlement as well. I was just curious if there's a concern about settlement, what I guess what design elements can you change or impact to reduce that? Is there something that?
Yes. Definitely. So there are multiple things we look at. One of them is the construction schedule. So as we're building it, settlement is happening, from the first time you apply the first layer. So that's one of the considerations. Also the embedment, when we remove the soils and we embed the walls deeper, that helps. So.
Okay, that makes sense.
And
then my
also,
last one.
we look at the remaining settlement, after construction. That's really what we're concerned with.
Mm-hmm. No, that makes sense. And then my last one, Fadi, is kind of something you touched on at the beginning. You said you worked on the battleship. HVJ worked on a battleship project. I was just curious as to, what that was and what you all did over there.
Yeah, so this was the Texas battleship, and I think it was used in either World War One or World War Two. I don't remember. But anyways, it's a cool project. So we had to design for, we had to do different types of analysis for seepage, uh, you know, and also like building sheet piles. Uh, it was a very unique project where, you have a unique structure that you have to carry, and global stability and seepage were the main concerns designing for it.
I take it you were out there, obviously on site at the battleship. Did you get to
I
visit?
wish if I was able to go. This was done through our Houston office, actually.
Oh, okay.
But I was involved in it. I was, asking for pictures and things, and keeping up with it.
Yeah, that's a cool one to put on your resume for sure.
Yeah.
Yeah, well, again, that's all I have, Fadi. But I want to thank you for for doing this presentation for us, and look forward to maybe doing something else with you and HVJ in the future. So
It's,
thank you
it's
very
my
much.
pleasure. Thank you so much for the opportunity to present this project.
Thank you.